So that should be all familiar to you. That's technically all review, all old stuff that we've done. Right? We know this. Yes. We're going to not do continuous variables this unit. We're going to do discrete random variables. So what that is talking about, over to the side here, discrete. No pictures in this part, no boxes or anything like that. A couple of formulas. So discrete, this is a distinct set of values. For example, age in years. So with age, you're not going to define that as being continuous. You're going to say, oh, you're 17, you're 18, you're 60, whatever age you are, okay? You're not going to say, I am 17 years, 82 days, 17 hours, through, like, you're not going to break it down into such small information, okay? It's going to be a distinct set of values. All right, so our center on this is the expected value. A lot of times you'll see it written as like E of X, or expected value. Okay, this is mu of X bar, which is equal to the sum of n equals 1 to I of X sub I times P sub I. I will explain, I promise. So jot it down and then I'll translate. Yeah. Yes, XI P I.
Is this an equation?
You're like, is that? Yes, that is. But I'll show you how to do it all on your calculator. No, I is not an imaginary number here. We're not dealing with that with our probabilities at all. It's just saying n goes from 1 to whatever it ends at. The x, that's just like the value we're talking about, so like someone's age. And then the p is the probability of that value occurring. We're going to find what? Sorry. Nope. And we'll do a bunch of examples with this, and this will make even more sense. But you basically just take whatever the possible outcome is times its probability, add all of those together, and that's your expected value. That's your mu. Okay? Spread. All right, we've got sigma squared. Remember, that's our variance. Again, we've got another summation here. N equals 1 to I. Yeah, sorry. Again, if you can't see it, please don't hesitate to ask. So we've got the sum n equals 1 to I of x sub I minus mu quantity squared times p sub I. Again, your calculator will do this for you. So what the spread is talking about here, you've got your individual value, that's the x sub I. You're figuring out how far away it is from the average, and then you're taking that times the probability, adding those all together to get your total spread. Okay? Again, you're not going to have to do this by hand.
Can you say that one more time?
Yeah, so the x of I, that's like your individual value. So you're kind of looking like how far away is that from the mean? Which that's what we're talking about with spread, is like how spaced out is everything. So how far it is from the mean. In the formula, you have to square it. And then you take it times the probability, because that's how likely that like event is to occur. And then you add all of those together to get the actual spread. Okay?
Okay, thank you.
Yeah. Yes. Yep, same thing. All right, shape, guys, there's no specific shape when we're dealing with probability. It varies depending on the spread of the probability. So there's no like, this is always this kind of graph. It's going to completely vary. So you can just say varies. For the probability calculations, what you're going to use a lot of on your calculator is the one variable statistics, so one var stat. That will be your friend this unit. All right, so let's do an example, and hopefully this will help the expected value and spread, everything make more sense to you. So we've got the game show Deal or No Deal. This guy's trying to figure out the expected value of the case he picks. The long-term probabilities here, he should break even. And this contestant has the $10, $100, $5,000, and $100,000 case. So let's set up our like table that we want to use in our calculator. So our X's, that's like the money he could win. So he's got a $10 case. He's got a $100 case. $5,000 and $100,000. So those are the 4 cases he has left, like suitcases that he has left. What do we know about the probability then for those? It's just 1 out of 4 for each of them, right? It seems like, oh, the probability should be less likely for the one with a lot of money in it, but we're not starting at the beginning of the game. We are saying, here's the 4 suitcases left. You have a 1 in 4 shot of picking any of them. So 0.25 for the probability for each one of these. Okay, if you were going to do this by hand, you would take the case value times the probability, add that up, and that would give you your expected value. If you're not doing it that way, we're going to do this on your calculator to save you a little bit of time. So go ahead and grab your calculator. Let me get mine opened up.
Wait, if you're doing it by hand, all you do is multiply the case value by 0.25?
Yep.
That'd be it.
And then plus each one. Yeah. So it's not that bad, especially when you only have 4 numbers.
Yeah.
If you have a lot of values, it's a little more painful. Okay, guys, I need to put values in a list. Where do I go? How about stat? And then I can edit a list. So stat, edit. So I'm going to put the 10, 100, 5,000, and 100,000 in there. And then what do you think I'm going to put in list 2? Yes. 125, 25, 25.
You always put your X values in list 1 and your probability in list 2?
I mean, you could switch them if you wanted to, but then when you did your 1-bar stat, you'd have to switch things around. So I'd be consistent and yes, do it that way. All right, everybody have them in? Okay, I need to calculate the one variable statistic. So how do I do that? Okay, and how do I get there? Do you remember? Stat, yep. Calc, good. Yes. Okay, your list, mine is in list 1 for the dollar values, right? That's where the money is. I am going to use the frequency list this time. So I'm going to put my probability list, which for me was list 2, in the frequency list. And you can do that by pushing second and then 2. That puts list 2 in there, or whatever list yours happens to be in. And then I'm going to go down and push calculate. And hopefully yours looks something like that. A lot of information, right? Anybody calculator troubles going, those are not the numbers I heard. Okay. Okay. What number up here is my expected value? Which one?
The second one down.
Which is the same as the first one, right? Yeah. You're like, yeah, it is. Yeah, so usually you're going to look for the X bar. X bar is your expected value. So that $26,277.50. So we're going to jot that down. So E of X. I'm going to make a note. That's my X bar. And that is my 26,000. Was it 277? And 50 cents, okay? So does expected value mean, oh, this contestant is walking away with $26,000? No. Is there any way he even could walk away with that much money? No. He's going home with either 10, 100, 5,000, or 100,000. But this means in the long term, this is the average amount that people would end up with.
Is this the number they give them? Like when they give them people?
Oh, so they do, like, think about that. Yes. This is figured in. Yes. Look at that math in your everyday world.
Every day, as the banker on Deal or No Deal.
Yeah, it's a requirement to be the banker on Deal or No Deal. You have to understand expected values, okay? Got to go, all right, they have down to 4 cases. Here's what I should offer them.
Imagine they just have their gap.
And they're like, hold on, let me see. We'll give you this much money.
Wait, so this is the same as 100,000 times 125 plus.
Yep.
Oh, that's actually.
Yep. That's it. Yes. Yeah. Nice when you kind of see it. And you're like, oh, okay.
Yeah.
Now, the standard deviation, I think, is harder to sort of visualize than the expected value, but you had that on your calculator. So, guys, what number up here is our sigma? Sigma. Good job, guys. Not a trick question. So, 42,611 and 57 cents. So, your sigma, X bar. So guys, with a sigma that large, that is showing you that there's a lot of variability in how this goes, right?
So the expected value is just the mean.
Mm-hmm. Yep. All right, questions so far? And again, you won't have to do those by hand. You can certainly use your calculator. Yes.
Large sigma means.
Oh, hold on one second. What? We will look at that, and then you just put in your list the different probabilities and calculate it that way. Yep. One of our other examples will do that.
So like a different probability of
Right, yeah, it's still, you still just type it in and say, go do that for me, thank you. Yeah. Sigma? Is that what you're asking?
Yeah, would you say large sigma means
like there's a lot of variability in how this goes, which makes sense on the game, right? Like you have people win very little money and you have a few people win a lot of money, and there's huge spread in between those values.
Thank you.
All right, guys, let's turn the page. Okay, so continuing on with this, we're going to talk about binomial distributions and geometric distributions. These are very specific ways to look at variables. We are going to look at a few conditions with these too. So this page is a pretty wordy page of notes. We'll get through this one and then we'll do some examples where it'll make more sense, okay? So hang in there through this one. So I'm going to do some conditions up here first. And this is for both binomial and geometric, okay? So each outcome is defined as success or not success. And you can write not in front, or you can put the little apostrophe afterwards. You could put the C from your test, remember, that's complement. So that's success or not success. So whatever it is you're looking at, it's either like flipping a coin and you want a head. Head is success, tail is not success. Okay, that's how the events have to be, or outcomes have to be defined. Second, each event is independent That's not success at the end. That's what the little apostrophe means afterwards. You can certainly just write not success if you're like, what? I don't know what that symbol means. That's fine. All right, each event is independent of previous events. So like flipping a coin, does what you flip on one turn have any impact on what you flip on the next? No, they are independent of one another.
And
And-
these things we will check before we do the problems, like normal conditions.
Yes. If they ask for it. You won't always have to do it, but this is like what has to be in place to actually do the binomial or geometric distribution.
Okay.
Okay. And then the third one is that the probability of a success, so P of success, is constant. Flipping a coin every time, assuming it's a fair coin, you know what that probability is. Okay. Squeeze those guys in. I'll give you a second here, make sure you're caught up. You're going to have to get good at figuring out, is the question a binomial distribution question or is it a geometric distribution question? So let me write,
What was this?
that's just like expected value.
Oh, it's a totally different.
Totally different thing. That's just like, what is your X bar of this? Here we're going to talk about like, how likely is it that I flip a coin and get a tail on the 3rd out of 5 flips of a coin? That
So
sort of
would
thing.
this be kind of like a step in one of these types of problems? or
Usually
no?
separate.
Okay, it's just a different type of question.
Yep. All right, guys, so the description for binomial. With this, the number of events is defined So, for example, not an example, just what you're looking for is we are interested in the number of successes in a certain number of events. Again, you can't read something fast. Yeah.
What you wrote.
That's all part of the description. This is what a binomial distribution question will look like. Well, it'll be something like, we want to know the probability of, you know, you're flipping a coin, something out of, like, 4 tails out of 10 flips of a coin. We want to know how likely that is to occur. That you know exactly how many times you're going to flip the coin. Like, that is defined up front. Okay, that's the key to it.
So will they define what a success is? Or will
Mhm. It's usually defined for you, yeah. All right, your center, your mu of x, is just n times p. Probability, and we'll look at your number of successes, all of that stuff. I'll show you this in an example, and it'll make a lot more sense. We do have a lot of p's. NP. I feel like my N needs a little, like, thing on the left. I know, it looked like an intersection. The intersection of just P. All right, and your spread, your sigma of x, is equal to n times p times 1 minus p. And your shape, as we talked about before, varies. And again, just get the formulas jotted down. I will go through them with numbers and an example, and it'll make more sense, okay? You will not have to figure out any of these calculations by hand. Like if I'm asking you something about flipping a coin 72 times, you're not going to have to write out like, oh, the likelihood of this 72 times. You can use your calculator for this. You will be using either the binomial PDF or the binomial CDF. So let me give you an example of what each one would look like. I'll do the example part off to the left and then what you type in your calculator on the right. So for PDF, it might say something like getting exactly 7 successes, whatever that is defined as. Out of 20 trials. Whereas binom CDF might say something like 7 or fewer successes. Out of 20 trials. Mm-hmm. It's just asking a different question. Yep. So it's looking for a very specific thing, like exactly 7 successes. What's the probability that I flip a coin and get tails 7 times out of 20 flips. That's what I'm looking at. In binom PDF, the PDF means point, whereas the C is talking about cumulative. So if you think about it, the PDF, we're looking at exactly 7 successes, like one very defined value. CDF, it's something cumulative. It's 7 or fewer. So it's 7 or 6 or 5 or 4 or 3 or 2 or 1 or 0. Like it's all of those things combined. So that's why we use CDF for that one. Does that make sense? So exact, very specific, that's the PDF. Something cumulative is the CDF. Okay. So on your calculator, you're going to have to put in number of events. You'll have to put in the probability of a success. And for PDF, the exact number of successes. CDF, you do, again, number of events, probability of success, but then it's the number of successes from 0 to your value. So if it's written 7 or fewer, you would put a 7 there because that's 0 to 7, right? Where it gets tricky is, what if I ask you for 8 or more? You can't put in 8 because that's going to give you from 0 to 8. So that's where we have to do the 1 minus this certain probability, and we'll look at examples like that. But this, you're always putting in 0 up to some number is what it's giving you the probability for, okay? All right, so that was all for binomial distributions. We also have geometric distributions. We're not going to write the conditions again because they're the same as they were up above. But let me give you the description this time. So for this one, we stop the process after the first success. The number of events is not defined ahead of time. So the key word you're looking for with geometric distributions is first. Like, it'll ask you something about probability of, the first head or tail or whatever your events are. That's what you're looking for to know that it is a geometric distribution. All right. Center, spread, and shape. What do you think I'm going to write for shape? Varies. Good work. Okay, center. Your mu this time is 1 over p. And sigma for geometric is the square root of 1 minus p over p. Again, jot them down and we'll look at them. We're almost through the long page, guys. Okay, we've got PDF and CDF again with geometric distributions. So PDF, it's a little more specific. It might say something like the first success on the 5th try. So if we're flipping a coin, flipping a tail, your first tail occurs on the 5th coin flip. What's the probability of that happening? Whereas CDF might be worded first success by the 5th try.
Wait, examples for like at the 5th try?
What?
Like what is the first success and the
On. Sorry, that's an O. On the 5th try. Do you see the difference between those wordings? Okay. First one, it's point, very specific. It has to happen exactly on the 5th try. Second one, it could happen on the 1st, 2nd, 3rd, 4th, or 5th try. Okay. For both of them, what you're putting in your calculator is probability of success. And then first success. Yeah, like when does the first success happen? But by you picking PDF or CDF, it's going to tell you something. All right, guys, questions on anything on that page? Okay, turn the page. Let's try to actually use this so you can figure it out a little better. It's the same for both. Yeah. So you're entering the same information, but picking PDF or CDF will tell you a different answer. Okay, guys, let's look at our example here. So we've got a certain type of plant. Guys. Sylvia, can you put it away, please? Thank you. All right. We have a plant, 85% of the seeds germinate, and a farmer plants 20 of those seeds. What's the probability that exactly 17 of these seeds germinate? Okay, first, we need to figure out, is this binomial or geometric? Thoughts?
Binomial.
Binomial. Who votes binomial? Who votes geometric? Okay, it is binomial. The reason it's binomial is this 20. We know exactly how many seeds are planted, so we have this defined number. So that's how we know it's binomial. Okay, then it says, what's the probability that exactly 17 of these seeds germinate? Do you think that is PDF or CDF? PDF. It's this very specific point of 17 of them. So you're going to do binom PDF on your calculator. And let me pull up my calculator to show you what it is. So guys, it's in the distribution menu, so second bars, that's where all your PDF and CDFs are. And then binom PDF for me, it's way down there. It's choice A for me. I don't know what it is on your calculator exactly.
where do we get this second?
Second bars. And then we're picking Binom PDF. And it leads you through this. So how many trials are there? Oh yeah, question. Yes, yes, exactly. So guys, how many trials are we having? In other words, how many seeds are planted? 20. Okay, what is the probability of a seed germinating? Yep, 0.85. Okay, what do you think the X value is? 17, and I have 220 here. So. Yeah, we want to know exactly 17. So push enter. Did you get 0.243? Yes. Okay, you've done part A. Good job. I'm just going to jot down the 20, comma 0.85, comma 17. And I got 0.243. So there's about a 24% chance that exactly 17 of these 20 seeds will germinate. Okay, next one. What is the probability that less than 12 of these seeds germinate? Do you see how that's CDF, not PDF? Because that would be anything from 0 to 12 or 0 to 11, right? Okay, so this is Binom CDF. All right, so let's go back to your calculator. Back into that distribution menu and go down. Always Binom CDF. So how many trials are there, guys? 20. We're still planting 20 seeds, right? Okay. What's the probability? Did it change? Okay, 0.85. All right, what is your X value? It is 11, okay? It's because it said less than 12. That means don't include the 12. That means up through 11 of them germinate. So we're going to put 11 there. Pretty low probability, right?
We're doing 11 as X value?
Yes, because it says less than 12. If you did 12 as your X value, that would include the 12th one germinating, okay?
So what is your X value?
11.
Oh, and then because it's CDF, the calculator knows you mean from 0 to.
Exactly. Yes. Yeah, that's why picking CDF instead of PDF. And so we got something like what, 0.001? Okay. And that makes sense. If it's an 85% germination rate, 11 or fewer of them actually germinating, that makes sense that that'd be pretty unlikely, since we would expect 85% of them to germinate. Okay, so that's how you use the PDF and CDF for binom distribution. Mu of X. Remember, we have a formula. What is it for mu of X for binomial?
Equals N times P.
N times P. So what is N? 20. What is P? 0.85, okay. And we get 17. So guys, what is that 17 telling us? Like the expected number that would germinate? Yeah, it's saying like we think if 85% of them germinate, 17 seeds will germinate, which is really very simple when you think about it. Don't make that harder than it is. It's just how many seeds are we planting? What percent should germinate? Here's our total number of seeds we think will germinate. They're very similar, yeah. This is just set up in a different way than the first expected value was, but it's what it's it's telling you very similar information. All right, guys, sigma, we had a formula for that. What was it? Square root of what?
N times P times 1 minus P.
Good. NP times 1 minus P. So that'd be the square root of 20 times 0.85 times 0.15. What do we get?
62.
All right, so I'm going to call that 1.6. That's just the spread of your distribution here.
Will we ever? Well, how we did before.
Mm-mm.
So the spread is just like to state it. It's not
Right, it just might be something I ask you. Like, here's what it is, yeah. All right, we okay with that first binomial example? Okay, let's look at the next one. We've got an old lawnmower, and it starts 20% of the time that the cord is pulled. Part A, what's the probability that it starts on the third try? Okay, yes. This is the geometric one, right? Like I didn't say, and we are pulling the cord on the lawnmower 7 times. We don't know. It just says 20% of the time it starts when the cord is pulled. So this is geometric. Do you think part A is geometric PDF or CDF? PDF, right? Exactly on the third try. That's PDF. So you're doing geometric PDF. Let me pull up the calculator. Again, back to that distribution menu. Keep scrolling. Ah. And no, that's not Poison, PDF, and CDF. We don't do Poison in here, but don't worry. All right, so I'm going to pick PDF. All it asks for is the P and the X value. So what's the P? 0.2. Yep. And we want to know probability that it starts on the third try. So what do you think my X value is? 3. Don't make this harder than it is. Calculate it. Are you getting 0.128? No? Okay. 0.23. That was 0.128. We're okay so far. All right, the last one's the trickiest. Probability that it takes more than 10 attempts to start the mower. When you do CDF, it starts from 0. I don't want the probability of 0 to 10. I want 10 and then continuing on. So we have to think of another way to write this. And I'm going to write out these numbers. You don't have to if you don't want to, but just to help you visualize it. So more than 10 attempts. Does everybody agree that that would be this group from 11 continuing on? Like that's the group we actually want. Yeah. Okay. So we could think of this as saying at least 11. Does anybody remember, we talked about it a little bit last unit, when you see the phrase at least, what do you need to do? 1 minus, yeah, 1 minus not that. So we're gonna do 1 minus less than or equal to 10. I know that's very poor math, like notation there, but at least 11 is the same as not 10 or less, right? Okay, so we're gonna have 1 minus. I'm gonna do geometric CDF for the up to 10, okay? Because that's what we can do with with the CDF. We can do 0 up to some number. We can't start at a number and go past it. All right, so let's look at your calculator. You should be able to just do 1 minus and then go into your VARS menu or your distribution menu. You can get to the geometric CDF by just scrolling up too. That's quicker than scrolling down all the way to the bottom. So I know the P is 0.2. What do you think the X value is? 10, yes. Okay, because we said less than or equal to 10. All right, so I'm putting that 10 in. And we are getting 0.107. So there's about an 11% chance that it takes more than 10 attempts to start the motor.
Wait, so what's the X value?
10? Does it make sense why it's 10?
Mm-hmm. Yeah.
All right, so we did 0.2 to 10 equals 0.107. Guys, that's one of the trickiest types of questions in here. Does it make sense to you? Okay, good. Just remember, you can only go from 0 up to a number. All right, guys, turn the page. Heavy side, we can do this. Yeah, sure. A brain break?
Yeah.
Will you come back from your brain break? I'm always afraid I'm going to just lose you when I give you a brain break. Sure, take a minute here. You're welcome.
So when you do 1 minus something, it kind of just means not.
Mm-hmm. Or it means at least this much. The at least means not,
At least not.
yeah. At least 11 means not 0 to 10,
Yes.
right?
Yes.
Okay. Takes a minute for that to sink in. Are we ready? I don't know if Lily's ready, but. Well, actually, I think I know she's not. All right, good. Back to it. Okay, guys, we can transform and combine our random variables here. Sounds scarier than it is. It means like changing your whole set of values by, we're going to add 10 seconds to everyone's time, or we're going to double the value of the suitcases, like that sort of thing. We can change in that manner. So you can learn new things, like so you can have different information. Okay, so we're going to do one with like swimming times. And maybe you want to know, like, if everyone swam 5 seconds faster, here's what we know about these different things. Like, some of it's very simple that you're like, I can just subtract 5 from everyone. But that's to help you see if you have a large set of data, what does an adding or subtracting number do versus what does a multiplying number do. Okay? Hang in there. I'll get you to an example here in a minute. So your basic transformations, if you're adding or subtracting, graphically you can think of this as a shift. Like you're just shifting the entire set of data values, left, right, up, down, something like that. So you're shifting. This is a shift. All right, Lily, put the phone away. Or whoever's phone that is, I don't know. Okay, guys, so think if you have a whole set of data values right here. We add 10 to everyone's score, and it shifts this way. What do you think has happened to the mean?
Increased by 10.
Exactly. So the mean increases or decreases, depending on what you're doing, by the constant. Yeah. You see these types of things on the SAT and all that good stuff. So
Would you ever have to do one of this where like one of these where it would be like not all of them increase by the same amount or anything like that?
no, we'll do. That's a totally different type of question. That's just not shifting or transforming.
Okay,
Yeah.
That seems a lot more complicated.
It is. Yeah. This is not that bad. Okay, guys, so let's visualize it again. You've got your set of data, I don't know, your test scores or whatever, and then bump everybody up by 10. We know the mean increased by 10. What about the standard deviation? It was here,
Stay the same.
and it went here. Yeah, the spread doesn't change, right? Because you added 10 to everyone. So if you're just adding or subtracting, the standard deviation stays the same. Okay, if you are multiplying or dividing by some constant, this is considered a stretch. This is algebra 2. It's okay. I won't make you graph it, I promise. We aren't going to like suddenly look at parabolas and stretch them by 3 or promise. So think again, let's say we have your test scores, and instead of adding 10 to everyone's score, I just say I'm going to double your score.
Oh, that was so good.
What would happen to the mean? It would double. Yes. Okay. So the mean, you just multiply or divide by the constant. Okay, for the standard deviation, let's think about this. Let's say my initial scores ranged from 0 to 100, and I doubled it. Now what do my scores range from?
0 to 2.
0 to 200. What happened to the spread?
Increased by 2.
It also doubled, right? So standard deviation, if it's multiplying, if it's getting stretched, it also stretches. Okay, so it's the same thing. Multiply or divide by the constant. So hopefully that makes sense how it's different adding and subtracting versus multiplying and dividing. We're not writing anything for the general rule, so we're jumping down to the combining random variables. So there may come a time where you need to actually add two separate distributions together. When you do that to find your new mean, you just take the mean of one plus the mean of the other. So mu sub 1 plus mu sub 2. And I'll show you this with examples too, so it makes more sense. Standard deviation, our sigma of whatever our combined mu1 plus mu2 is. Do you guys remember what we did with this before? We can't actually add standard deviations. What can we add together? Variances, yeah. So I add the two variances together, and then I can take the square root of that sum.
Can you read what's under the?
Yeah, that's totally scribbled. Mu sub 1 plus mu sub 2.
Okay. That makes more sense.
Is adding
There we go.
distributions, is that like adding new files or like?
Kind of, but you'd usually use like your final results, like whatever your mu was from group 1 and mu from group 2, and then we combine them. Or you might only be given that information, and I'll say, what's mu1 minus mu2? And what's the new sigma of those? That sort of thing. Just very like algebraic-y kind of questions. All right, so we have to do the sigma of our first group squared, because that's the variance, plus sigma of the second set of values we have here squared. So that's adding the two variances and then taking the square root to get the new sigma. We've done that before, but it's been a while since we've done that.
Why don't we just add this again?
You can't add sigmas. I know it seems weird. You can't just add the standard deviations. What's going to get even weirder for you is subtracting. We don't subtract them, we still add. All right, guys, if we're subtracting whole distributions here, the mean you just subtract. You do mu1 minus mu2, or whatever the order is. Standard deviation, though, do you think we subtract the variances now? We don't. You can only add variances. Okay, so whether it's an addition or a subtraction, to find the new spread, you're still adding those two variances together. Okay, I know it feels wrong. So if it's mu1 minus mu2, it is still sigma of the first one squared plus sigma of the second one squared. Feels wrong, looks like a typo, it's not, okay. Okay, I want to squeeze in, I think you guys have room at the bottom to squeeze in a little example down here.
We stop after this or do we?
We'll see, probably, we got 10 minutes left, guys, we'll see. All right, you are given this little box of information here. You're given the mu and sigma for these two different distributions. One I'll call x and one I'll call y. Mu of x is 10, and the sigma for x is 2. And for y, the mu is 20 and sigma is 5. All right, so I'm going to ask you some questions, just to practice all of these different transformations. Let's say I asked you for mu and sigma of 3x. So 3x, what is the mu? What is the sigma?
Just think variance.
30 and 6 is exactly right. Right? When we're multiplying by a constant, you just take the mu and the sigma times that constant. Okay, so the new mu is 30 and the new sigma is 6. You guys see what we're doing now? Okay. All right, what if I asked you what is y plus 6? What is our new mu and our new sigma going to be? We're adding a constant this time. What do you think, guys? Yes, mu is 26. And you're not doing sigma. Luke? 5, yes. Remember, if we shift by 6, we just increase it all by 6. That doesn't change your spread at all. Okay.
We have,
So that was the original sigma for y distribution, right?
yeah. Oh, because it doesn't change.
Yep.
Sorry.
You're fine. No, I'd much rather have you ask than sitting there going, why? Okay, we're going to add distributions together. X plus y. What is my new mu? My new sigma. Give you a second to think about this one. Yeah. The new mu is 30. That one's not too bad, right? We could just add them together. What about the new sigma? It's okay if you have a square root in your answer.
Square root, okay.
Yes. All right, let's stop there for a second, make sure we're all okay with that. You're like, nope, not okay with that. Okay, you see the two sigmas, right? Our 2 and 5. So we'll add. So this isn't given to you, but could you figure out the variance for each of them? So this one would be 4 and this one would be 25, right? You just square the sigma. So then to find your new sigma, remember you take the two variances, add them, and then the square root of that. So that's how we got to square root of 29.
Oh, I see.
See it? Okay. Everybody okay with that? Are we sure? Yeah, let's wait a sec. That's okay. Sure. So are you okay with the mu being 30 for... Okay, part C, x plus y. Are you okay with the new mu being 30? Okay. Sigma, square root of 29. To do that, remember we take the variance for each. So if your sigma's 2, that means your variance is 4. If your sigma's 5, your variance is 25. Okay, we just square those numbers, add them together, and then take the square root. Yeah. All right, let's try again. How about we do x minus y? New mu, new sigma. Yes. Square root of 29, yes. You're really close on the mu. It'd be negative 10, yeah, because if you actually do x minus y. Yep. Oh, okay, that's all right.
Wait, why is this over 29?
Remember, it feels
Oh,
wrong,
oh,
but
you
you
square.
still add. Yeah, you square them and add them still, even though
Okay,
it's the
so you
difference.
just square it to the negative with the way. Or is it just...
Well, there's not really a negative.
So basically... This is...
You're just adding, yeah. You're always adding to find the new sigma. All right, one more with this little set of info here. What if I do x plus x? New mu, new sigma. Think about it. This is it. This is it on this page, I promise. Looking very skeptical right now.
It's like so simple that I don't know if I'm overthinking it or like I don't know if I'm under. You know?
Thinking level, what is it?
Yeah.
All right, what's the new mu, guys? 20, right? We're just doing 10 plus 10. Okay. Sigma. It is the square root of 8, which is 2 root 2. Because you actually have 4 and another 4? Okay. So it is 2 root 2. Give me the decimal, I don't care. All right. Okay, guys, we will stop there, and we'll start. We just have a few more examples, no more like crazy definitions and things like that, okay? So we will stop here and jump back in on Thursday.